Hi, I'm Dominik Steinhöfel, and in this talk, I am going to show you how you can use my tool Refinity to prove properties of statement-level Java program transformation rules. The first part of my talk is already the demo. In the demo, I will target one particular such transformation rule. It's a refactoring rule called slide statements, and I will show the conditional correctness, that is, the property of the rule to preserve the semantics of its transformed input program, given that certain preconditions are met. So let's switch over to the window of the key program prover. Key is a program prover for Java based on symbolic execution, into which I integrate a framework for reasoning about abstract programs. When you open Key, you are presented the window that you see here, and down there under abstract execution, you see slide statements, and there you can go and just have a look at the example that I'm now going to develop live on stage. All right, but we'll start from scratch here, as I said. On the top control bar of the Key window, you find this button here with the Refinity logo. Just click on it and Refinity will open up. Refinity is essentially a front end for Key for proving relational properties of programs. That is, you have a program on the left and on the right hand side here, and you can prove, for instance, that the result of the left hand side is the same as the result of the right hand side. We start with something really simple. So assume that you have a program which assigns 17 to a variable x and 42 to a variable y in this order. And now you want to swap these two statements and prove that the result is still the same after doing this transformation. The variables x and y here are global variables because I want to compare them on the left and right hand side. So we need to declare them in Refinity. And for this, we have this little control on the top left. And you see already when you hover over the control with your mouse, you are presented a tooltip explaining what this thing does. So whenever you feel unsure about something in the Refinity window, just hover and you will be helped. So I will add now an integer variable x and an integer variable y that Refinity now knows, which we can now reason about. And reason about means that I want to declare those variables as relevant locations that I want to compare, which means to show their equality after execution of these programs. So I add both x and y to relevant locations on the left and right hand side, so for both programs. And I leave the default post condition saying that these things should be the same after executing both programs. So when I now hit the play button that you see here, Refinity creates a proof obligation in Java dynamic logic for the key prover. And you see that key is doing some things. So it's registering some rules and loading the proof that Refinity creates, and also already starting the automatic proof search. This problem here is now really simple. Key finishes to prove the correctness of this transformation within 119 nodes. And now I could also save this proof and use it as a certificate for my already existing model using this certification button here. So of course, in real programs, it rarely happens that you have an assignment of 17 to x and 42 to y in exactly this order. So the rule that I modeled here, that it's okay to swap these things, is not really the most interesting thing you could think about. So what we want to do here is we want to use abstract execution to prove something more general. Abstract execution is a framework for reasoning about abstract programs, and this means that you can have statements and expressions representing an basically infinite number of concrete statements and expressions. What you do is you type abstract underscore statement and you give the thing a name, for instance, P, and you can do the same thing for another statement that you call Q, and then you swap these on the right-hand side and try to prove equivalence. So because usually, such a general transformation is not possible, at least not if you want to have a semantic equivalence. You need to constrain the represented concrete instances of your abstract statements and abstract expressions that we also have to those that behave well, basically. And for this, I will use specification statements written in the Java modeling language. The syntax that I use here is a little lengthy, but Refinity has editor support for this. So I simply need to type AS and hit Control-Shift-Space, and I get a stub with an abstract statement P and some specifications. What these say is that P may assign some set of locations called frame P. By convention, I call assignable locations frame and locations that are read footprint. And those, the footprint, are defined in the second line. And the remaining 4 lines just tell us here that for this model, I don't expect my instances to complete for any reason which is not normal. So for instance, they will not throw an exception. So I have one abstract statement here working like a set, and now I define myself another one that I call Q. I adapt the names of these abstract location sets. And now, similarly to the broken variables that I had before, X and Y, I also need to declare these frame P, footprint P, and frame Q, footprint Q, which I do using this control down here. So frame P, footprint P. That's a little work to type all these things. And the same for Q and its footprint. Footprint Q. All right. You see that in the bottom of the window, my relevant locations vanished because I deleted X and Y, and of course, now something else should be relevant. And since I am modeling an abstract scenario here, so I am swapping statements with arbitrary frames and footprints, I also don't want to commit myself to some concrete variable that should be equal afterward, but I want to say that the whole state should be the same before and after the transformation. And this is done by just using a location set with no particular constraints. So there is already a predefined one called relevant here. And unless I impose something on this set, it could be anything. And so if I leave the default post condition, I have to prove full equivalence on the resulting state. All right, so now I write my second program into which I just copy paste my statements in reverse order, and I can try to prove this with key. This will take longer now, and also it will not succeed. Just a remark on the time needed to prove this. I want to stress the point here that what we prove here is a result which is true for an infinite number of concrete statements. And when applying this to a particularly concrete program, we just need to instantiate this scaffold. So the proof that I'm now doing only needs to be done once, and this effort is well invested. So after 1,217 rules, key finishes, and we have one open goal. And there are a number of problems here that we can now try to read from the proof that from the proof goal that remains open, and feedback to our model to finally obtain preconditions that make our transformation actually semantics preserving. So this is a lot of complicated syntax here. In essence, what needs to hold is that the contents of this predicate P and this predicate Q here should be the same. So there are a number of issues here that we can see by having a close look at what there is. So first, you see that here is a state update corresponding to our statement Q. And it assigns to its frame, so the frame of Q, the original value of the footprint of Q, while down here, we have another update corresponding to our statement P on the footprint. And indeed, this can happen. So P might write to the footprint of Q while it does not have this chance after the transformation. So back to our simple example, if we have X equals 17 and Y equals X, then when swapping this, we see that the value of y will be different afterward. So we need to impose disjointness on the frame of P and the footprint of Q. So P must not write to what Q reads and vice versa. To do this, we declare an abstract execution constraint using another Refinity shortcut here, saying that we need to have disjointness of what I said, of the frame of P and the footprint of Q, and also vice versa. So I copy paste this frame of Q and footprint of P. So when I now run the proof again, we will have another open goal. For time reasons, I'm going to skip this. But instead, I will go back to the proof here. And we see that in addition to this slightly different shape of the state updates, we also have a different order of the updates in the state. So here Q updates before P, and here P updates before Q. And also this is a real problem. So if you have, for instance, a program where you assign 17 to X and then 42 to also X, then swapping this will override the effects of the first statement, of course. So what we need to do in addition is to impose disjointness of also the frames of P and Q, so that P must not override the changes issued by Q. So let's do this quickly. Frame Q, so there should be no typos now in this live situation. All right, we need to paste this also to the other program, since they are basically regarded in isolation. All right, so this should suffice, and if I'm not wrong, Key should be able to prove this thing automatically within reasonable time. And now when trying to swap statements in a particular concrete program, we need to show that the locations corresponding to the instantiations of frames and footprints here are disjoint like I specified. So this proof is a once and for all result for the slide statements refactoring rule. And you see that Key manages to prove the thing. So we're done here. Of course, we could now go and generalize our model by also considering abrupt completion. But for time reasons, I will now instead switch over to my presentation. All right, Refinity already has been applied to a number of interesting case studies. What you have seen here now, slide statements, is a code refactoring rule. There are a number of such refactoring rules that I studied. It has been published at Formal Methods 2019 and to a broader extent also in my PhD thesis. And what you see here on the slide is another such refactoring which replaces a try catch by an if else. It also has a sudden pitfall that I found by reading failed key proofs and feeding things back to the model. And this was, so to say, the flagship application of abstract execution and Refinity so far. So you can also have a look at different properties than semantic correctness of transformations. For instance, you can have a loop and extract a loop invariant statement to before the loop. And what we did with a group of the University of Madrid is to prove that this transformation really reduces, or at least not increases, the cost of executing these programs here. This work has been submitted to FASE 2021, and so let's hope it will get accepted. Starting from the same situation, you have again this while loop here. You can also do a different thing, split the loop into two parts under certain conditions, of course, so we can prove with Refinity that under preconditions, this is semantically safe. And now we can go ahead and run these loops in parallel, which is done by our collaboration partners. In this paper here, another group of the University of Darmstadt. And this has been accepted to ISOLA 2020 and will appear soon, or I think maybe it has already appeared. All right, so now I have shown you all these nice things about Refinity. So you might want to download the tool, and you easily can. So just go over to this web page here and download it. And when you open Key, you are, as I said, presented the examples dialog, and you can play around with all these models of Java code refactoring rules. Maybe you learn something about conditional correctness of refactoring also when having a look at this. There is documentation in Refinity apart from the tooltips that I've shown you before. I have this webpage here where you'll find some more information on using the tool. So this is under ongoing development, but there's something already now that you can read. And if you really want to dive deep into abstract execution and also have a more detailed account on Refinity, the tool, you can read the respective chapters in my PhD thesis, which you can freely download under this URL. This already leads me to the conclusion of my talk. I've presented Refinity to you, which is a tool for relational verification of abstract programs. And since you can view pairs of schematic abstract programs as rules, you can prove the correctness of or properties of transformation rules on statement level Java programs, statement level transformation rules for Java programs with the tool. Refinity generates non-trivial proof obligations to be proven, discarded by the key program prover, and it also supports certificate checking. So once you have a proof, you don't need to run everything from scratch. Once you want to check where your model is okay, you can just reload and replay a once generated proof. Refinity has a number of measures to support you in editing abstract programs. So there are shortcuts, syntax checking, tooltips, and what have you. And a little bit of ongoing work is that I'm working on automated instance checking. So this problem that you have a concrete program and you want to check whether your abstract model represents this program such that you can apply the transformation you modeled and obtain the correctness results. All right, this was my talk. I hope you enjoyed it. And I would enjoy to have some new followers on Twitter after the talk. Thank you very much.